Zoom fatigue. There we go, the recording's going. Yeah, and myself included, it's nice because we can all have these meetings kind of remotely without having to travel, but also I know how tedious they can get when you're just doing Zoom after Zoom. So I appreciate you calling in today. I'm actually in Ontario right now. We drove north from DC where we live. It's sort of, we make like Canadian geese in the summer and escape the heat to Georgian Bay. So we're up here on pretty good Wi-Fi this year, but if it gets a little bit finicky, just let me know and I can always repeat if or cut my video if need be. Okay, but without further ado, let's talk about LiDAR, which is what we're here for. So yeah, I'm presenting this on behalf of myself and a large number of people, and many of whom are not listed on this slide, but these people in particular provided figures or inputs for this presentation. So I'm going to be focusing on GEDI, but also ISAT2, especially there are some people doing boreal stuff, and of course GEDI doesn't collect data north of 52 latitude. So as Canadians, we are also interested in this other LiDAR mission. So I'll talk about both of those. And this is really kind of focused on forest structure and biomass mapping and monitoring. But of course, there are other wonderful applications of these LiDAR systems, and so happy to go off in tangents to discuss anything else too. Okay, so you all know this, but just to remind ourselves why we care about forest structure and biomass, right? So with the Global Carbon Project, like general global carbon cycle, we know how much CO2 we're pumping into the atmosphere from fossil fuel emissions. We know how much is staying in the atmosphere, and we know that the forest and the oceans are this wonderful natural sink of CO2. But the largest uncertainty in any piece of this is of course, particularly how much carbon is being lost due to deforestation and degradation at this whopping 61% uncertainty. And that is because we don't know how much carbon is stored in Earth's forests to begin with. So we can see from Landsat when we lose forest, more or less, right? But we don't know how much is being lost when that land conversion is happening. So that's where GEDI and ISAT2 are coming in, is to finally make a good three-dimensional map of Earth's forests and hopefully have accurate biomass numbers so that when we see forest conversion, we know how much carbon more or less is being lost from that conversion. So hopefully we can reduce this uncertainty. But then of course, as we have these better carbon numbers, hopefully we can actually manage our forests to reduce the loss as well. So that's just a reminder for those of you, but I'm sure everybody on this call is like, yes, we know, we understand the importance of forest structure and biomass. Okay, so from a mission perspective, here is the GEDI mission way back in the before times in 2018. GEDI was launched to the International Space Station. So here's a subset of the GEDI science team. Ralph Dubaya with the gray ponytail in the back there is the PI of GEDI. And this was originally a 2-year mission. So it started collecting science data in April of 2019. And it's already gone through that 2-year mission. So now we're working into an extended period of collection, which is great. So the lasers, everything's going well. As long as they don't boot us off the ISS, GEDI will continue to collect data until those lasers fail.
We lost her.
Sorry, did you lose me?
Yeah, but keep going.
Okay, I apologize. That might happen a couple of times, and I'll just cut my video if it happens again. Yeah. But we're sharing Wi-Fi. We're up on this like remote island, so it's kind of, anyway, hopefully it's okay. Yeah. All right, so GEDI is in orbit. Oh, sorry, Arturo, how much did you lose from this?
Nothing. Just keep going. That you guys were there, and Dubaya was there. That is the guy with the crazy hair, and that was it.
Okay. All right. I'm going to cut my video just because that tends to be the issue, is more upload than download, but we'll see if this works. Sorry about that. Okay. So GEDI is in orbit. Oh, hopefully you can hear me. And I'm going to play this automation, but I don't know how well it'll play. Hopefully you can see this. So here is the International Space Station where GEDI is housed. And GEDI is about a refrigerator-sized box plugged into the side of the International Space Station. So it's got 3 lasers. One of them is split into 2 beams, and those 4 beams then, so the 2 power lasers and the 2 coverage beams are optically dithered to create 8 ground tracks under the ISS. It's got about a 4-kilometer swath, and there's about 600 meters between those ground tracks and about 60 meters between GEDI pulses along each of those tracks. And each individual laser pulse illuminates about a 25-meter diameter circle and returns a LiDAR waveform, which is this orange squiggle here. So this is probably old news to many of you who are working with things like Elvis, but this is the core GEDI measurement are these waveforms. So then we take these waveforms and we translate them into estimates of topography elevation, canopy height, and canopy cover, leaf area index, and ultimately biomass. And so biomass is really what I'm going to be focusing on today. And I'm going to be risky and try and start my video again. We'll see. It's when my video starts freezing that I know that that I might have lost the audio too. But okay, hopefully this is working again. All right. Next slide. Here we go. So for those of you who are not familiar with waveform LiDAR and might have used a lot of airborne LiDAR, this is something that I get a lot of feedback on, is that that when you start working with GEDI, people are kind of disappointed because they think like, oh, satellite LiDAR, it's going to be giving me this amazing 3-dimensional point cloud everywhere on the planet, which of course is not the case, right? So the core observables really are these waveforms, and they're this sparse sample of the Earth's forests again, right? Like 60 meters along tracks, 600 meters between tracks. At this point, we have more than 10 billion cloud-free waveform observations, or sorry, more than 10 billion are expected. We're more than halfway toward that 10. I think we're at like 5 or 6 billion at this point. And as I said, the science collection started in April 2019. So we've been going for more than 2 years now, and we're expected to continue until at least the fall of 2023, I believe. Right now, there's some negotiation going on. The level 1 and 2 data products are online. So for each waveform, translating it into an estimate of ground elevation, and then the relative height metrics, so like the canopy height metrics and canopy cover metrics, those are all online already. And the level 4A, which will be the footprint level above ground biomass, that's going to be online like any day now. And that's what I'm going to be focusing on today, is telling you what that product looks like and is all about. Are you hearing me okay now? Just want to check in.
Fantastic.
Yes.
Fantastic.
Awesome. Okay. Just wanted to make sure I wasn't giving a presentation to nobody because of my Wi-Fi. All right. So as I said, GEDI is not a wall-to-wall mapper, right? And most of you probably know this because you maybe had some experience with the data. But as you download the data, you're going to notice that you'll see something that looks like this spatially. So you get these 8 ground tracks, and 4 of them are coverage laser data and 4 of them are power laser data. The coverage laser, it's literally like a full power laser has been split into 2 beams, which are each a little bit less powerful than the full power, or than half of the full power laser. So the full power laser can penetrate up to like 99% canopy cover, super dense forests. If you're like in a little bit of doubt, maybe the coverage laser data is looking a little funky, you can just focus on the full power laser data. In places where there isn't super dense canopy, the coverage laser data is fine as well. If you're using daytime data, you're going to have some solar kind of noise, right? Like there's near infrared photons bouncing around all over the place, especially during the day. So there's going to be a little bit more noise in the coverage laser data during the day. Like the best possible data is the full power laser data during the night. But there are ways to filter out the data. Most of the ecosystems in the planet, you can use all of this and it should be okay, just using the quality filters in the data sets. Okay, so here's a quick look at the global gridded topography products. You can see the ISS orbit's kind of funky. It's not like your sort of typical Landsat MODIS type orbit because it's on the ISS. So it's sort of the squiggly thing that turns around 52 degrees north and south. So it gets like southern Canada, it actually blankets it with LiDAR data, and then goes to literally nothing above 52. Okay, so this is what the gridded topography looks like. This is essentially a grid of the elevation of the bottom of those waveforms. And then you get canopy height by taking the top of the waveforms minus the bottom of the waveforms. It gives you the height of the trees. And so that can be gridded as well. over time, GEDI is going to fill in more and more and more collections. So the gridded products are going to get better and better, higher accuracy in filling in the data gaps that exist. This is the data after 1 year of collection. Okay, but biomass is kind of like our bread and butter, and that's the product that I'm a co-lead on. So that's what I'll focus on today. So how are we translating these waveform squiggles into estimates of above ground biomass? And so for those of you working in things like machine learning or quantum mechanics or anything fancy, we're being extremely simple here. So this is like super, super simple empirical models. Okay, so what we've done is we acknowledged pretty early on in the mission that we were not going to be able to go into the woods and measure trees in GEDI-sized plots co-located with actual GEDI waveforms during a 2-year mission length all over the world, like a small team with a relatively small budget as far as NASA is concerned. And so we're like, okay, that's impossible. How are we going to make this translation, right? We're not directly measuring biomass. We measure waveforms. We need to train, field plot estimates of biomass to create our models. So instead, we've like begged and borrowed data off the community, including Arturo, who's wonderfully generous with us. And so anyone who has field data with co-located airborne LiDAR, we then take those, as long as they're collected at the same time and place, and we take the airborne LiDAR and we simulate GEDI waveforms from it. So we build up this simulated GEDI waveform database over field plots. So even if they were collected 20 years ago, if they had LiDAR 20 years ago, we can use that as a training point, and then we build our empirical models that way. So it's not perfect, but it's pretty good. And also just to acknowledge the fact that we're not actually directly measuring biomass in the field. This is a cartoon that a friend of mine drew for my PhD defense, which was kind of focused on allometry stuff. And so we're not actually weighing the trees, right? We're measuring their stem diameters, their heights, et cetera. We're applying these allometric models. So there's a lot of uncertainty in them. I will just acknowledge across the board, we are not accounting for allometric model uncertainty in GEDI's biomass estimates of uncertainty. We're ignoring it. Everybody else has ignored it. It's like the community's dirty little secret. And we're certainly trying to address this and improve this moving forward. But for the first round of biomass models, you're going to have an estimate per footprint. It's going to have a standard error that does not include the allometric model uncertainty. Okay, so here is the database that we are building the models based on. Some of this is publicly available data from sites like Neon and Turn in Australia. Some of it is privately, so it's like managed by research groups or companies, and we've written a data sharing agreement so that we're using it for GEDI, but we're not releasing their data or anything like that. So this is the database that we've compiled. This is actually a little bit outdated now. We're getting more and more data, especially in the boreal, which I'll talk about in a little bit for ISAT-2. But this is where we've taken field plots in airborne LiDAR, simulated GEDI waveforms, and built biomass models. Okay. And so when you're doing this kind of work at a global scale, you have to think, okay, like we're not making one biomass model to rule them all. We tried that. And we're like, can you make one conversion of waveforms to biomass that's globally applicable? Turns out, understandably, no. I mean, you can, but it's not going to be as good as accounting for the natural variability in forests, right? So, but we couldn't go too detailed because if you break the world up into two specific geographic strata, we run out of training data. So we kind of came up with this happy medium in the product by dividing the world up by continent, or we call it geographic region, which is the top right here, and by plant functional type from MODIS, which we have then subset into 4 very broad categories of evergreen broadleaf trees, needle-leaf trees, deciduous broadleaf trees, and kind of this catch-all of other stuff, which we call woodland, grassland, shrubland, or GS here. So here's the biomass distributions of our training data on the right in these different geographic strata. So essentially, we take all of our training data from like evergreen broadleaf trees in Africa, and we make a model there. And so for all of the GEDI shots in evergreen broadleaf trees Africa, we apply that model. So it's super simple. And so what are the actual predictors? Like, how are we translating the waveforms to biomass via these empirical fits? We use the relative height metrics from the lower level products, from the level 2 products. So these are the height below which some proportion of the waveform energy has been returned. And they're loosely comparable to percentile height, except that they include the ground portion of the waveform. So like RH98 is the height below which 98% of the waveform energy has been returned. It's equivalent to the maximum canopy height for the GEDI footprints. And so here we looked at which predictors, which RH metrics were being selected for. And we found that kind of across the board, across these 4 different PFTs, maximum height was being selected, and some like kind of low portion of the waveform was being selected. So RH10, RH20, we think that this is kind of a loose proxy for canopy cover because we're not considering canopy cover in the first round of the GEDI biomass models. We will consider it in later rounds. But yeah, it was interesting, like across the board, it seems like no matter what ecosystem you're in, maximum height is important, and something about the bottom of the waveforms is important. That makes sense. We all know that as you have taller and taller canopies, you have more and more biomass. So this was a nice little sanity check as well. So I just wanted to quickly walk you through what this actually, like, this is how simple it is. It's so simple. So you take a waveform. So this is like one of our models, for example. This is a model for the South America evergreen broadleaf trees. And this is actually, it's been a little bit updated since I made this slide, but it's roughly the same as this. And so you have a waveform here, and you pick in the waveform where the ground elevation is. So this is from the lower level product algorithms from the level 2 product. So you say like, essentially this last peak in the waveform is where the ground is. And so everything above that is representing reflection off the canopy. And so if you're just calculating the RH metrics here, for this model, RH20 and RH98, so like the top and the something about the bottom of the waveform are used as predictors in this basic, very basic OLS model that has a square root transform of the height metrics and of biomass. So it's a square root transform model. So then for this waveform, the RH98 is 29 meters and the RH20 is 4 meters. So you literally just plug that into this equation, and then you back transform it and do like a bias correction because it's the square root model. And for this waveform, you get an estimate of 146 tons per hectare of biomass. And I'm not showing the uncertainty estimation here because like nobody needs to look at that on a Wednesday afternoon, but that's essentially what we do. We just take, for every single waveform, we do a lookup table of which model to apply, and then we just apply it. And it's just basic OLS with RH metrics. And so we just repeat this like 10 billion times, and that's the product. And then we take all of those shots, the 25-meter shots, and all of them in each 1 kilometer pixel, we average them. And so our biomass products are at a 1 kilometer resolution. These ones should be forthcoming in the next, I would say, like month or so. And so the footprint level will come out literally any day. The gridded biomass, I would say, in about a month. With an uncertainty map as well, which is super important. So these are all the products that will be online. Either they're online now or they'll be online in the near future, are these gridded versions as well as the shot-by-shot data. So please take them, interrogate them, improve them, do stuff with them. This is what we're here for. Okay, so that's all the GEDI stuff. But of course, let me just do a time check. Yeah, I'm good. Okay, of course, GEDI doesn't get into the boreal forest, really. It just gets like the little southern edge, which as Canadians is depressing. So fortunately, we have another NASA LiDAR mission that went up just a little bit before GEDI, ISAT-2, which will essentially fill in the rest of the pie here. So toward truly global biomass mapping, we can combine GEDI and NASA's ISAT-2. So this is ISAT-2, which is a totally different type of LiDAR, which, as you could probably guess, is not designed for vegetation because it's literally called ISAT. But it's great in the boreal. It's great. If you get into too close to canopy, the ISAT-2, it's a photon counting LiDAR. It's using green LiDAR. And if you're in a too dense a canopy, the photons have a tendency to not sample the ground. So they kind of underestimate tree height in a really dense canopy, or if you're in too sparse a canopy, the photons tend to not sample the top of the trees. So in general, ISAT-2 kind of shrinks the trees a little bit when you're too sparse or too dense, but in your kind of like a Goldilocks mid canopy cover sweet zone, ISAT-2 is great. And a lot of the boreal falls into that sweet spot. So it's great. So this is what ISAT-2 looks like for those of you who haven't worked with this. It's kind of like a really noisy point cloud that goes forever in a transect. So the actual ISAT-2 laser Each pulse illuminates about like a 12 or 13 meter diameter circle, but from that circle, they only return like 1 or 2, maybe 3 photons. So like almost nothing. But then it moves along track just 70 centimeters and it does the same thing. So you get this like super, super rapid progression along this forever transect of ISAT2 data, which gives you something that looks like this. So this is actually from BC. And so this is like this noisy transect photon cloud that we process to estimate canopy height metrics, just the same way as GEDI, but like the LiDAR and the actual data itself is like totally different, but useful. Okay, so for each of these, in a 100 meter segment, there's an estimate of, they call them relative height metrics. They're a little different than GEDI, which I'll get to in a second, but it's like an estimate of maximum mean canopy height, the ground elevation, et cetera. So each of this is a product called ATLOB from ISAT2, and each 100 meter segment has a suite of canopy height metrics associated with it. So this is kind of what the data looks like. So there are some places where you miss the top of the canopy, some places you miss the ground, but like is pretty good compared to nothing else, because GEDI doesn't cover anything north of 52, right? All right. So we have a separate project that kind of complements GEDI that is, well, it's actually 2 projects we've kind of merged into one bigger project, but one is through NASA's Arctic Boreal Vulnerability Experiment, which studies the North American boreal. And so we are making an ISAT2 map for that domain, but then we have since, and sorry, I'm kind of leading that project, but then we extended it through the ISAT2 science team with Amy Neuenschwander to make a boreal wide product. So essentially we're trying to take GEDI up to, 52 and then fill in the rest of the boreal with an ISAT2 biomass map. And we're trying to take a very similar, very simple empirical approach using field plots, using airborne LiDAR. So it's like kind of like the approach we took for GEDI, but we use ISAT2 data instead. And of course, there's a lot of nuance in how we process the LiDAR for that. So the main things here are that if you're just trying to take ISAT2 kind of out of the box and apply a GEDI-like biomass algorithm to it, it's not going to work because even though, and this is, if any of you have used both ISAT2 and GEDI, you're probably like, what? They're called relative height metrics in both products, but they're totally different. So it's really confusing. And we kind of tried to push against them calling relative height metrics, but we failed. So GEDI's relative height metrics are the height below which some proportion of the waveform energy has been returned, including the ground segment. Like the ground part of the waveform is included in the calculation of these relative height metrics. The ISAT2 classifies every photon as being from the ground or from the canopy. And so its relative height metrics are more like percentile height metrics from discrete return LiDAR. And so it doesn't include the ground photons. So automatically there's going to be like a bias between the height metrics, which we've totally seen. And then also, of course, so that's like the first issue. The second issue is that there are different canopy penetration capabilities, like GEDI, the power beam especially, can get through like the densest canopies on the planet, whereas ISAT2 really can't. So it kind of shrinks the trees a little bit. And then of course, these are different spatial resolutions, right? So like maximum height in like a 1 hectare plot is on average going to be taller than maximum height in like a 30 meter plot, just because there's a higher likelihood that you're going to have a taller forest the larger the area you're looking at. So all of these together, it means that you can't just like simply treat ISAT2 like it's GEDI. There's some nuance there. Through our research project, we are making ISAT2 more GEDI-like. So we're creating a 30 meter version of ISAT2 right now for the boreal, but we could do this globally. And then we're recalculating the RH metrics to include the ground photons. So we can't fix the fact that sometimes ISAT2 just doesn't see the ground or doesn't see the top of the canopy. It's always going to be a little bit noisier than GEDI, a little bit error, probably a little bit of a low bias of height. So on average, it's underestimating height and biomass a bit, but we can change the other things to make it more GEDI-like. So that's what we're doing for the boreal. We're making like a GEDI-like version of ISAT2 at a higher spatial resolution, and then we're actually linking it to Landsat for 30 meter wall-to-wall mapping in the boreal. Okay. So then that's my sort of spiel about the products themselves, GEDI and ISAT2. So now I'm going to talk a little bit about other things, and hopefully I don't lose the plot and bore you guys, but these are sort of some of like the forward-looking issues of how we're going to improve these products moving forward and what kind of science we can do with them. So of course, maps are only as good as the data used to train them, right? So we know that there are issues with these data sets. One is that like they're just big spatial data gaps. So like Central Asia, we have no idea how good we're going to do there. We're like borrowing data from other geographic domains and applying it there. So as more data are collected through GEDI's very small CalVal program, but through other CalVal programs, we've launched a new initiative called GeoTrees, where we're trying to we're hoping that like the private sector can start contributing to some big CalVal campaigns, because biomass is so politically relevant. Essentially, if we can reduce the uncertainty in our products, it actually has like economic value. So we're hoping that the relatively small cost of doing big global field campaigns and airborne LiDAR campaigns can be covered by, who knows, Jeff Bezos, if you're listening, like we'll take your money for this. But yeah, so we've got to fill in these data gaps, and we also have to improve the data there. So I told you that we're ignoring the allometric model uncertainty. I've got a new GEDI science team grant where we're trying to look at alternative allometric models like from terrestrial laser scanning, and seeing if we can swap them into the whole GEDI CalVal training database, and then see if our models get better just because we're using either non-allometrically estimated field biomass or TLS allometry biomass estimates, instead of the sort of traditional general ones like Shaw and Jenkins and Ung and so forth. Okay, so that's one exciting kind of progression. And I know your lab does a lot of TLS work. So I really feel like for biomass, the strength here is going to be swapping in these allometries, or in a dream world, sending TLS all over the world and like making allometrically independent estimates of biomass. That would be the dream goal. So here's like a little bit of eye candy from Atticus Stovall, but I'm sure you guys are all very familiar with this type of data from TLS. Just sometimes it's nice to like toss on some nice visuals on some of these presentations, but like the level of detail you can get, as you all know, from TLS versus these more, is that here? Let's do a second one, versus like the sort of just measuring the DBH and the height of these trees. Now we can like literally reconstruct them in 3D. The uncertainties will just totally reduce. And I'm imagining that the biomass models that we have for GEDI will have lower uncertainty if we can swap out our traditional field approaches with TLS. So that's like a kind of a long-term goal, I think, of the entire community, is to try and have more and more TLS data and hopefully improve our field estimates, because that is driving a lot of the uncertainty. Okay, so that's like one thing, TLS. It's super exciting. We all love it. Let's keep doing that. Then also just acknowledging that that GEDI and ISAT2, these are sample missions, right? They're not wall-to-wall mappers. And so for the vast majority of applications, people want the wall-to-wall data. So GEDI makes a wall-to-wall product at 1 kilometer by aggregating all of like the samples within the 1 kilometer cells. For ISAT2, we're extending it with Landsat. But I think the best biomass maps moving forward are going to be a combination of LiDAR and radar. So I'm like, I don't know, a rebel against the LiDAR community a little bit here, but LiDAR is always going to be very important, but a lot of people, they just treat LiDAR like training data, right? And so for the wall-to-wall maps of the future, with the NASA ISRO's NISAR mission, which is a L-band SAR mission, which will be collecting global L-band SAR every 12 days. ESA's biomass mission, which will be P-band SAR, so it doesn't saturate as at as low a biomass density as the other ones. There are all of these time series of SAR data coming forward. So both NISAR and biomass will launch in 2023. It's going to be like an explosion of data. And I think the LiDARs will really serve largely for training data for those SAR missions. So this is very exciting. We're also kind of almost overwhelmed with all the potential new data sets. So those are just like naming a few, right? So here are some of the SAR and LiDAR missions that are relevant for biomass now and in the future. And I hopefully, maybe I'm optimistic, but I think that we're not going to like all of a sudden not have satellite LiDAR. There's going to be some future iteration of GEDI on the far horizon. JAXA has MOLI, which is a similar full waveform LiDAR mission that's been proposed to go to the International Space Station after GEDI's done. So like looking forward, it's like if we're drowning with data now, it's only going to get more exciting and more confusing in the future. So we in acknowledgement of this like sort of imminent chaos of all of these different biomass relevant satellites, of course, we're going to have all of these biomass products coming out. So like GEDI's making one, but I know almost every independent big research group is making their own version. The private sector are making their own versions, often using the satellite data, but like with their own training data, with their own fancy machine learning algorithms, et cetera. So, and that's great. Like we want the best products to be out there, but how are we going to know what the best products are unless we have a way to transparently and globally compare them? So we wrote a protocol, which is kind of like guidance for how to make a good map and guidance for how to properly use a map. And it's like the CEOS Biomass protocol, which we released this spring. So if you want some light bedtime reading, here's 200 pages of like statistical equations for you. But this is kind of like a mega review paper on biomass mapping. So if you are looking for something to help you write your lit review for your dissertation, please use it. There's a lot of summary in this document. But we're trying to actually bring that document to life now. So this is like super new. We, as like kind of a biomass mapping community, are recognizing that, hey, like even with our like relatively small group of researchers, we're making multiple biomass products, and we're going to confuse everybody almost immediately. So we've got GEDI's biomass product that'll be released this year. We've got through Sasan Sachi's group, he's got a couple different biomass products coming out as well. Some of them use GEDI, some of them don't. CCI Biomass through ESA has a series of biomass products representing different epochs. They're making a new product. And then there are like a smattering of other biomass products that are coming out of the woodworks. We're like, okay, we're about to confuse everybody. Let's try as a community to actually bring all these products together and compare them transparently, harmonize them, and release all of the source code that we use to do so. And so we have just launched, like in the last few months, a biomass harmonization activity with the goal of providing one single map to rule them all, or at least one recommended map for the UNFCCC's 2023 global stocktake, which is essentially like the UN after Paris saying like, hey, how well are we doing as a global community toward any of our Paris agreements? So all of the countries will say, hey, like we curb deforestation by blank and our emissions are up or down by blank. They need data sources across the board. So biomass, forests are a big part of the Paris Agreement, and biomass is an important part, arguably the most important part of climate sort of commitments from a forest perspective. So trying to give them a product that we as like a remote sensing community have all signed off on is highly desirable. So this is my last slide, and then I'll turn it over for discussion. But I just wanted to highlight kind of the way that I see our community moving in the future, which will be very relevant to particularly to students. So this is like what I've heard somebody very senior at NASA call the future of science at NASA, is all cloud-based open science. So NASA obviously has an open data policy. All of our products become open, but now we're transitioning to an open science policy, and it hasn't been written in stone, but this is certainly the direction we're moving, where if you put out a biomass product right now, you don't have to release the source code. So we can put out 10 biomass products from different groups, and if they don't match, everyone's going to get confused. And if you can't look under the hood and see how the products were actually made, like what is the training data, what is the source code, can I reproduce this myself, then that confusion will not go away. So the idea here is to, anytime you make a biomass product, but probably any NASA product, you'll have to release the source code. And because all of the NASA data is now transitioning to the cloud, specifically Amazon Web Services for now, but who knows what the cloud compute of the future will look like. But as we're making products now on the cloud, the source code will be released with the products, and it'll be linked to the compute systems that made the products, so that theoretically anybody could reproduce any product that comes online from NASA. The European Space Agency is moving in a similar direction. So this slide here is this new open science platform called the Multi-Mission Algorithm and Analysis Platform. This was a bilateral platform design between ESA and NASA. It's just leaving its pilot phase, so we're going public like in the next few months with this thing. I'm a project scientist on it. I'm one of 2 NASA project scientists to kind of like advise the development of it. But I'm really excited about this because, I mean, I'm sure many of you, like, you read a paper, you're excited about some algorithm, and then you're like, oh, there's no code here. I can't actually try and use what this paper is suggesting. And then you like come up with your own hacky version. I'm a self-taught programmer, so it's not like necessarily efficient. And, you know, so if I could actually see the code that somebody wrote, accompany a paper and a product, that would be way more useful, right? So here, this is a cloud-based compute infrastructure that's linked to all of the NASA data. So like GEDI, ISET2, et cetera. The pilot was really built around biomass mapping, but I think that this is going to become kind of like the standard for all of these different communities as well. And the idea is, yeah, essentially to bring full transparency to the biomass mapping entire community. So this is something to maybe look out for. Essentially, you like just use a web browser like Google Chrome. You can then search for data. You can write algorithm. You can write code collaboratively with a bunch of your colleagues. We're using this platform to make our boreal Y biomass map. So all of the source code will be available for that one. And we're also using this for the biomass harmonization activity. So, so this is something I'm excited about and I wanted to share with you all, but stay tuned for that. Okay, so that's certainly enough of me nattering on at you guys. Thank you to Arturo for the invitation and for all of the wonderful data from Santa Rosa. And there are many other people internationally who have provided to the GEDI and ISET2 boreal biomass training data sets. So you can follow GEDI on Twitter at GEDI Nights. We really lean into the Star Wars theme, and my Twitter handle is here as well. So, okay, that's all I had. Thank you so much.
Thank you very much, Laura. Fantastic presentation. We really appreciate it. It has been a very important motivation for our group, and hopefully my guys will have questions. I'm going to stop our recording right here. And